Hello everyone. So in this lesson, we're going to be learning about the concept of inverse matrices. You might have noticed throughout this entire process, we were able to add, subtract, and now finally multiply. You might have noticed we never divided. And there's a reason for that. We really can't divide matrices. We can't do like one matrix divided by another matrix. It does not work. However, because math people are math people, they came up with a workaround. And here's the idea. Let's say I were to take this equation, ax equals b, this equation here, ax equals b. And if you were in like an Alg 1, Alg 2 class and I asked you to solve for x, you would always, like 99 times out of 100, tell me, hey, I would solve for x by dividing a to the other side, right? We would always say, hey, divide a to the other side, and we get x equals b divided by a. I'm going to throw out a different idea, though. Instead of dividing a, could I multiply a by its own inverse? If I multiply something by its own inverse, it also reduces. Typically, dividing and multiplying by an inverse are the same thing. The reason I'm bringing this up here is I can multiply this side by a inverse as well. Whatever I do to one side, I do to the other. And multiplying by an inverse is not exactly the same thing as dividing. So what that means is if a matrix has an inverse, I can get x by itself by multiplying by that inverse. A couple things worth noting that you never had to consider before. When it comes to matrices, the order of multiplication matters. Remember, the order of multiplication matters a lot when you multiply matrices together. In order for two matrices to be inverses of each other, if I were to multiply matrix A times A inverse, what I'm telling you is for inverse matrices, if these two matrices are inverses, the order shouldn't matter. And either way I do it, I should get I, my identity matrix. As a reminder, the identity matrix, if I did a 2 by 2 matrix, would look something like this, 1, 0, 0, 1, where I have ones on the diagonal and I have zeros everywhere else. So what that means is if I have two matrices, let's call them A and B, I can find out if they're inverses by multiplying them together and seeing if I get the if I get the identity matrix. This needs to work both ways for this to work. So I'm going to start by doing A times B. So I have matrix A, which is 1, 2, 3, 5. And I'm multiplying that to matrix B, -5, 2, 3, -1. For these matrices to be inverses of each other, first thing worth mentioning is there are, how do I phrase it? You can only have inverses of square matrices. Only square matrices can have inverses. So since these are both square, I at least have a chance. As a reminder, this is a 2 by 2. Being multiplied to another 2 by 2. So what that means is these can multiply, and I'm going to get a 2 by 2 matrix as a result. And I'm going to leave lots of room for this 2 by 2 just to make sure I have enough space. So if I want the element here in the first row, first column, I'm going to go first row and first column. So I'm going to do 1 times -5 is -5 plus 2 times 3 is 6. Now to get the element here in the first row, second column, I'm going to go 1 times 2 plus 2 times -1. The element in the second row, first column, is going to be 3 times -5 times 5 plus 5 times, what would that be? 5 times 3. 5 times 3. And then last but not least, this last one's going to be second row, second column, so that's going to be 3 times 3. Plus, oops, sorry, not 3 times 3. What am I saying? Not 3 times 3. That's going to be 3 times, second row, second column. 3 times 2 plus 5 times -1. If we simplify all 4 of those down, I'm going to get 2 plus -2 is 0. I'm going to get -15 plus 15 is 0. And I'm going to get 6 minus 5 is 1. So that means A times B equaled my identity matrix. But that's not good enough. I now need to do b times a. I now need to multiply b times a to check if these are inverses. So I need to take my matrix B, which is -5, 2, 3, -1, and multiply it to my matrix A, which is 1, 2, 3, 5. If they're inverses, I will also get the identity matrix. If these are inverses, I should get the identity matrix again. So first row, first column, again, I'm going rows in this matrix, I'm doing columns in this matrix. -5 times 1 is -5, plus 2 times 3 is 6. Here I have first row, second column, so I'm going to do first row, second column, -5 times 2, plus 2 times 5. Here I'm going to do the second row, first column, so I'm going to do the second row of 3, -1 times the second column here. 3 times 1 is 3, plus -1 times 3 is -3. And here I'm doing second row, second column. 3 times 2 is 6, plus -1 times 5 is -5. If I combine these, -5 plus 6 is 1, -5 times 2 is 10, plus 2 times 5 is, -5 times 2 is -10, plus 2 times 5 is 10, that works out to 0. 3 plus -3 is also 0, and 6 minus 5 is 1. So these are both equal to I, which means A and B are inverses. If either one of these did not work out to this matrix, they would not be inverses. Well, that's great, but how do we find inverse matrices? Let's say I were to just give you a matrix. Let's say I just gave you this weirdo matrix, 3, 2, 1, -1. And I wanted you to find the inverse. The process of finding an inverse by hand is kind of annoying. So here's the idea. I'm going to write out our matrix, 3, 2, 1, -1. 3, 2, 1, -1. And now I'm going to augment that with the identity matrix, 1, 0, 0, 1. Basically what I mean is I'm making my matrix bigger on purpose, where I'm putting our original matrix on the left, and I'm putting our identity matrix on the right. I'm putting what we're trying to turn it into on the right. Our goal, the way we're going to find the inverse matrix, is we somehow need to get this matrix over here to look like this matrix over here. We need this matrix on the left to turn into the identity matrix. And here's what I mean by that. So, for example, I think of it almost as a game. We first need to find a way to turn this 3 into a 1. So the very first thing I'm going to do is I'm going to do 1/3, oops, feel right, 1/3 times row 1 landing in row 1. All that notation is coming back. I'm going to do 1/3 times this very first row and put it in row 1. The reason being I'm trying to turn this 3 here into a 1. So that means my second row I'm going to leave completely alone. So I have 1, -1, I have my augmentation, and I have 0, 1. Here, if I do 1/3 times row 1, landing in row 1, 3 times 1/3 is 1, 2 times 1/3 is 2/3. Yes, you will have fractions. 1/3 times 1 is 1/3, and 1/3 times 0 is 0. The next thing I'm trying to do is I'm trying to get this 1 here below this 1 down here. I want to turn this into a 0. I want to make this become a 0 somehow. And the way I'm going to do that is I'm going to actually just do row 1 minus row 2. If I do row 1 minus row 2, that turns into a 0. So I'm going to do row 1 minus row 2 landing in row 2. I'm going to replace my row 2. So I'm going to leave my row 1 alone for now. So I have 1, 2/3, I have my augmentation, I have my 1/3, and I have my 0. Now I'm doing row 1 minus row 2. So 1 minus 1 is 0. That's the whole point of what we just did. Here comes the fun parts. 2/3 minus -1. 2/3 minus -1. Because the double negative there, it's going to turn positive. And if I add fractions correctly, this is actually going to become 5/3. 1/3 minus 0 is 1/3. And 0 minus 1 is -1. So it might not feel like it. We did achieve our goal. This value here became a 0. Now our next goal is to turn this number here into a 1. We want to somehow turn 5/3 into a 1. The way I'm going to do that is I'm going to multiply 5/3 by 3/5. If I do 3/5 times row 2 and put it in row 2, that will turn this element here into a 1. My row 1 I'm not touching right now. So it's 1, 2/3. There's my augmentation. I have 1/3 and I have 0. I'm going to multiply each element here by 3/5. So 0 times 3/5 is 0. 5/3 times 3/5 is 1. 1/3 times 3/5, if you be careful there, I'm actually write this one out. 1/3 times 3/5, the 3's reduced and I'm left with 1/5. And 3/5 times -1 is -3/5. Okay, we're almost there. And yes, inverses will have this many fractions. Yes, they will. It does happen. It's just part of the territory. The last thing I need to do to make it so that my original matrix here looks like the augmented matrix, I need this 2/3 here to somehow become a 0. To do this, I'm going to take 2/3 times row 2, or sorry, -2/3 times row 2 and add it to row 1, specifically landing in row 1. I'm going to do -2/3 times this row and then add it to the top row to make a brand new row 1. My bottom row is going to stay the same. 0, 1, my augmentation, 1/5, -3/5. If we look here, -2/3 times 0 is 0, plus 1 is 1. -2/3 times 1 is -2/3, plus 2/3 is 0. We have achieved our goal in getting it to be 1, 0, 0, 1 to get the identity matrix. The only thing we have left to do is now these numbers here. So these ones I'm going to write out. I'm going to do -2/3 times 1/5, and I'm going to add it to 1/3. Right? I'm doing -2/3 times this plus that. -2/3 times 1/5 would be the same thing as -2/15 plus 1/3. To add fractions, we need common denominators, so I'm adding 5 here. If I do that, I would get 5/15 minus 2/15 is 3/15. And then 3/15 I can reduce into 1/5. So this would become a 1/5. Thankfully, this next one's not as bad. I'm going to do -2/3 times -3/5 plus 0. Adding 0 means I don't really have to do that. So -2/3 times -3/5, that'll become a positive 6/15. Or if I simplify that, that'll become a positive 2/5. So the reason we did all this is, what I'm saying is, if our matrix A is 3, 2, 1, -1, our matrix A inverse, very badly written, our matrix A inverse is the matrix 1/5, 2/5, and -3/5. This matrix that we have here on the right, this thing here, that is our inverse matrix. Okay, I hear you. That's too much work. There's no way we're ever doing that again. If it's a 2 by 2 matrix, I have good news for you. You don't have to. If it's anything bigger than a 2 by 2 matrix, this is the best way to do it, what we just did. But if it's a 2 by 2 matrix, there's actually a formula. So, let's say I had some matrix A, B, C, D. You might recognize this from when we were talking about determinants. And if AD minus BC is not equal to 0, aka, we didn't talk about this earlier, but aka, if the determinant is not 0, then the inverse matrix is just 1 over the determinant times now the rearranged matrix D, -B, -C, A. The way I think of it is that this A and D here switch places, and then B and C switch signs. So here's what I mean by this. Let's try this formula out. If I want to find my inverse matrix B, if I want to find B inverse, it's equal to 1 over AD minus BC times the matrix DA negative B negative C. So I'm going to start out with AD minus BC. I'm going to do 1 over, well, AD minus BC, that's just the determinant. 1 times 4 minus 3 times negative 2. 1 times 4 is 4, so I get 1 times 4 is 4 minus 3 times negative 2 is negative 6. I'm getting the determinant is 10. So I'm thinking this is 1 over 10. Times the matrix. All I do is switch D and A around. So this is going to be a 4 here. This is going to be a 1 here. And these two, I just change the signs. So this becomes a positive 2. This becomes a negative 3. And you know how to multiply a scalar to a matrix already. I'm just going to multiply this 1/10 to all 4 of the terms. So I'm getting the matrix 4/10, 2/10, negative 3/10, and 1/10. If you simplify some of these, you would get the final answer of 2/5, 1/5, negative 3/10, and 1/10. This is how to find an inverse for a 2 by 2 matrix relatively easily. What I'm saying is if I were to multiply B times this matrix over here, I would get the identity matrix. If you have a 3 by 3 or higher, unfortunately, this is the best way to do it. If you have a 2 by 2 matrix, you can take this really nice shortcut. In class, we're going to talk about how to do this in a calculator, because wouldn't it be nice if I gave you something like this and you didn't want to do it by hand, that we could do it in a calculator? So we're going to do that in class on that day. But if you have any questions, please let me know. Have a good day.